everybody. Well, not everybody, right? Because remember, 100% of cases are under the normal curve. We at least know that 99.74% of them exist between 3 standard deviations below and 3 standard deviations above the mean, which means that the difference between 100% and this 99.74%, which roughly calculates to what, 0.26% of the population, exists, beyond the 3 standard deviations below and above the mean. But we'll get into that more in just a moment. But suffice to say that this 9974 is intended to be representative of everybody within, 3 standard deviations below, 3 standard deviations above the mean. Now I'm going to apply a very quick, as quick as I can, try and convey this to you all in terms of thinking about this as it relates to a population related to a variable. Let's say that we are discussing the average male height. Average male height and I want to be specific about where I'm applying this variable or what population I'm drawing from. We're going to discuss this in the context of the average male height in the United States. So, the average male height, I happen to know this. I guess as a statistician, maybe I'm supposed to know this, or as a sociologist. Either way, the average male height in the United States is 5 feet 9 inches. Okay? Remember that each of these, these standard deviations represent units of distance. So in order to be able to understand what this average height means in relation to the rest of this normal curve, we need two pieces of information. One of them is the average male height, which we've just identified as 5'9". And then we also need the standard deviation of male height in the United States. I also know that the standard deviation of male height in the United States is 3 inches. Now, the only reason I'm not using female height in this particular scenario is because in doing research about average female height, the average female height in the United States is 5'3.5" with a standard deviation of 2.5. So the only reason I'm not using it here is because I don't want to confuse us with the half parts of height. So we're going to focus in on this particular example because these whole numbers make our lives a little bit easier for calculating these things by hand. So the average male height is 5'9" with a standard deviation of 3. Now, remember that this 68.26% represents percent of the population. So in order to find out what this information means for what percent of the population, or 68% of the population, 68.26%, what is the height that they exist within? Because when we have an average height of 5'9", this doesn't mean that every male in the United States is 5'9". Of course, we know there is variation in this. And so in order to kind of navigate this, if we understand that one standard deviation, remember that even if a number is not presented here, this then means that this is 1. One standard deviation is 3 inches, which means that every one of these standard deviation points on our normal curve represent at least to the right of our mean, they represent the addition of a standard deviation. So if we do some math here and we take our average height of 5'9" and we add to that one standard deviation of 3 inches, then someone, I'm just going to write this out real quick. I probably won't write another piece again because we'll just follow along as we're doing this. That's supposed to be a 9, not a 4. If the average height is 5'9", the standard deviation of male U.S. height is 3 inches. So 5'9" plus 3 inches equals 6 feet. So that means that at this point here of one standard deviation above the mean, we find males who are 6 feet. If we add another 3 inches to that in order to find out the height represented at 2 standard deviations above the mean, we find that the height here is 6'3". And then if we add another 3 inches to find out what's happening at 3 standard deviations above, we have a male at 6'6". Now, as we are able to apply this kind of formula to working to the right of the mean, then we can also use these same pieces of information to navigate what's happening on the left side of the mean. And in this case, instead of adding 3 inches, we're going to take that same height, 5'9", excuse me, and instead of adding, we're going to subtract. So 5'9" minus 3 inches is going to place us at 5'6". So the height at 1 standard deviation below the mean is 5 feet 6 inches. Even though we have a -1 here, that doesn't mean that we are suddenly working with negative numbers. It's just a representation of a movement relative to the mean. So we have 5'6". Someone who is 2 standard deviations below is going to be another 3 inches shorter in height, which we have 5'3". And then at 3 standard deviations below the mean, we have a height of 5 feet. All right, so we've just been able to apply our understanding of mean and standard deviation to this normal curve. Okay, we found out what heights are represented at each of these points along the x-axis of our normal curve. So as a reminder, the average is 5'9". Someone who's at 1 standard deviation above the mean is 6 feet. Someone at 2 standard deviations is 6'3", so on and so forth, right? We can continue this. Even though this particular illustration stops at 3 standard deviations above the mean, we can continue. And we know that if you've ever, I'm thinking about Ripley's Believe It or Not, right? The tallest people to have ever existed. We know that people can exist above 6'6", right? Remember though, the further away we move from the mean, the less likely something is to occur. And so even though it's possible to find someone at 4 standard deviations above the mean being 6'9", or 5 standard deviations above the mean being 7 feet, the further away we get, the less likely it is to happen. Which is why we have shows like Ripley's Believe It or Not, if you're old enough to even remember that, or the Guinness Book of World Records, where we're recording these, extremely rare instances of something occurring. And so, as it relates to height, those males who are that tall, 7 feet and above, statistically they are unlikely to occur, which is why we're fascinated by them in the first place, right? But kind of pointing out that we can continue moving to the right of this illustration of this normal curve and continue to find different heights represented there. And the same thing can be said if we were moving to the left of this normal curve, right? At 3 standard deviations, we have a male who is 5 feet, and there, in existence, we have males who are shorter than that, right? So we will get to 4'9" at 4 standard deviations below the mean, 4'6" at 5 standard deviations below the mean, and so on and so forth. And again, statistically very unlikely to occur, okay? Now, to tie it back into this idea of the population, remember that this 68.26% represents everyone that's happening here. And when I say everyone happening here, remember that we're talking about a distance between standard deviations. 68.26% of the population exists between 1 standard deviation below the mean and 1 standard deviation above the mean. If we bring in this variable of height and with the data that we've just been able to conclude based on our understanding of the average and the standard deviation, what this means is that 68.26% of males in the United States are between the height of 5'6" and 6 feet. Okay, that's how we, apply some social science and being able to draw conclusions from this kind of information. 68.26% of males in the United States are between 5'6" and 6 feet. And we can expand that out, right? Let's incorporate another color here just to emphasize a point. If we are now extending this out to describe males between 2 standard deviations below the mean and 2 standard deviations above the mean, our concluding statement would be 95.44% of males in the United States are between the height of 5'3" and 6'3". And we can continue this on and on, right? Discussing 99.74% and so on and so forth. So that's how we can apply a variable to this idea of the normal curve. Now, while we're working with height, there are other variables that we can use here. You may have heard before of being able to apply this type of probability theory and normal curve to the discussion of IQ. We could apply it to this idea of IQ. We can apply it to the idea of weight. We can apply it to the idea of like daily caloric intake, or the number of steps that you take a day, or GPAs even, right? We could talk about this in the context of community college student GPAs. Not every variable can conform to this idea of the normal curve. The ones that will work within this class, however, will be applicable to this idea. But just know that not necessarily every single variable can conform to the normal curve. So that's just an important piece of information. Okay, let's go ahead and going to remove this and let's move forward.